If you ask the smartest, the most advanced artificial intelligence in the world right now, a really simple question about your company's vacation policy,
Yeah.
it would totally fail.
Oh, absolutely. It would fail miserably.
Right. It would probably just hallucinate some weird generic response or, just politely apologize to you. And not because it isn't brilliant, it is,
Hmm.
but because it has the severe case of corporate amnesia.
Yeah, that's a good way to put it.
So welcome to the deep dive. Today we are taking a sledgehammer to the intimidation factor around modern AI. Because if you are listening to this right now, yes, you have likely been bombarded with just a relentless wave of acronyms over the past year or so.
Oh, the acronyms are everywhere?
RAG, LangChain, MCP, vector databases, embeddings. It's exhausting. And it creates this very real sensation of AI FOMO.
Yeah, that fear of missing out is huge right now.
Right. It's this creeping dread that everyone else has magically figured out how to build these autonomous digital brains. And you're still just trying to get ChatGPT to format an email correctly.
Yeah. Which is a universal feeling, by the way. I mean, that feeling of being left behind is so common right now, largely because the vocabulary of software engineering just evolved seemingly overnight.
It really did.
But the reality is actually far less magical than all this terminology suggests. When you strip away the jargon, the underlying concepts, they follow a highly logical, really step-by-step progression of problem solving. We are basically just addressing bottlenecks in how computers process human language.
Okay, let's unpack this because our mission today is to take you from absolute zero to completely understanding the end-to-end architecture of a modern AI agent. We are going to build this mental model together.
And we have some great source material to help us do that.
Yes, exactly. To guide us, we are relying on this massive, incredibly comprehensive masterclass guide from CodeCloud. It actually breaks down this entire ecosystem, but we aren't just going to read you a textbook today.
No, that would be terrible.
We are going to apply this to a real-world scenario. So throughout our conversation, we're going to build an AI assistant for a fictional company. Let's just call them TechCorp.
I like it. TechCorp is, well, they're the perfect stand-in for almost any modern enterprise because they are sitting on an absolute mountain of unstructured data.
Just piles of it.
Let's say it is roughly 500 gigabytes of internal documents.
Wow, so that's decades worth of material. Employee handbooks, HR guidelines, those deeply convoluted IT security policies.
Inventory spreadsheets.
Frantic memos from the legal department.
Right, 0.5 terabyte of entirely private, proprietary, and highly specific data.
And the CEO of TechCorp has mandated the creation of an internal AI chatbot. Because the dream here is that a new hire can just type a question into Slack and get a perfect instant answer based entirely on that messy internal data.
That's the holy grail.
Well, so where do we even begin? Because obviously we need a brain to process all this text, but the brain itself seems to be the initial bottleneck.
If we connect this to the bigger picture, to build any AI system, you absolutely must understand the foundational intelligence you are working with. And that means understanding large language models, or LLMs.
Okay, so we're talking about the big ones.
Right, the frontier models like OpenAI's GPT-4, Anthropic's Claude Opus, or Google's Gemini. The defining characteristic of these models is really just their sheer scale.
The massive amounts of data.
Exactly. They are trained on data sets so huge they're almost difficult to conceptualize. We're talking tens of trillions of tokens scraped from millions of different domains, spanning healthcare, law, advanced physics, literature, you name it.
It feels like they are incredibly smart. But really, it is just that they have read essentially the entire public internet. And that broad training is, I guess, what gives them their versatility.
Yeah, it is the scale of that reading that creates this illusion of human-like intelligence. They have mapped the statistical relationships of human language across almost every conceivable public topic.
But that brings us directly to the brick wall facing TechCorp right now. Because all of that brilliant training data scraped from the web, it explicitly does not include TechCorp's 500 gigabytes of private HR and IT documents sitting on a secure internal server somewhere.
No, it definitely doesn't.
So GPT-4 has absolutely no idea what TechCorp's specific policy is regarding, say, taking a company laptop across international borders.
The AI is a savant, but it is a savant with a massive blind spot regarding your specific proprietary world. So the first logical hurdle a developer tries to clear is finding a way to introduce that private data to the savant.
And the instinct for most people, My instinct is to just hand the AI the documents in the chat box. You open up the interface, type, here is our 50-page remote work policy, paste the whole thing in, and then ask, based on this, can I work from Paris?
Right, and that physical space where you paste your prompt and your data, that is known as the context window.
The context window. But
You can visualize the context window as the artificial intelligence's short-term memory. During a single active conversation, everything you type, everything it generates in response, and any massive text files you drag and drop into the interface, they are all held in this temporary cognitive workspace.
we have to talk about how the AI actually measures that workspace, though, because it doesn't think in terms of pages or megabytes, right?
No, not at all.
It measures capacity in tokens. For anyone trying to wrap their head around this, what physically is a token? Like, is it just a word?
Not exactly. A token is the fundamental atomic unit of data for an LLM. It's basically a chunk of text. For the English language, a generally accepted rule of thumb is that one token equates to roughly 3/4 of a standard word.
3/4 of a word.
So if you have a 1,000-word corporate memo, the AI interprets that as roughly 1,300 tokens.
Knowing that, how big are these short-term memory workspaces? If I'm building this TechCorp bot, how many tokens can I shove into the prompt before the whole system just crashes?
Well, the capacity varies wildly based on the specific architecture you select. If you look at the nano, mini, or flash models,
The really fast ones.
exactly, the ones engineered specifically for rapid response times and low computational latency, their context windows are actually quite restricted. You might be limited to somewhere between 2,000 and 4,000 tokens.
Doing the math on that 3/4 rule, that is only about 1,500 to 3,000 words. That is barely a single long-form blog post, let alone a whole corporate handbook.
Yeah, it's not much, but the frontier models push those boundaries significantly further. Anthropic's Claude Opus handles 200,000 tokens.
Wow.
xAI's Grok goes up to 256,000. And Google's Gemini 1.5 and 2.5 Pro models, they boast an astonishing 1 million token context window.
1 million tokens is staggering. The masterclass source material notes that is equivalent to roughly 7,500 words. Way actually looking at the source, that math seems a bit quirky.
Yeah, that calculation is definitely off.
Right, 1 million tokens would be vastly more than 7,500 words. The source clarifies later that 1 million tokens is actually closer to a massive library of books, or get this, up to 50,000 lines of dense, highly complex computer code.
It is an immense volume of text to hold in temporary memory. And there's a real economic reality to holding that much data that developers often overlook. Until they get their first bill anyway.
Right, the API costs.
In the masterclass labs, when they walk you through authenticating your Python environment and making raw API calls to OpenAI, they force you to examine the actual JSON response object that the server sends back.
I found that part of the lab totally fascinating.
Mm.
Because when you use ChatGPT on the web, you just see the text magically appear on the screen.
Yeah.
But when you build it in code, the text is buried deep inside this nested data structure.
It really is.
You actually have to write a specific path, I think it was response.choices.message.content, just to isolate the actual words the AI generated.
Right, and drilling down into that response object reveals more than just the text. It exposes a metadata field containing your precise token usage statistics for that single interaction.
Oh, so you can see exactly what you're paying for.
Exactly. You see a clear breakdown of prompt tokens, which represent the data you push into the system, and completion tokens, which represent the text the model generated in return.
And those completion tokens, the output, they are billed at a significantly higher rate than the input tokens, right?
Substantially higher. The computational burden of generating a new token is much heavier than simply reading an inputted token.
That makes sense.
This is why prompt engineering isn't just about getting a better answer. It is a critical cost control measure. Designing systems that constrain the AI to output concise, highly targeted responses literally saves TechCorp money on every single query.
Okay, but even considering the cost, let's go back to our TechCorp scenario for a minute. We have access to a model like Gemini Pro with this massive 1 million token window. Why can't we just take a huge chunk of our 500 gigabytes of company data and just dump it all into that window?
Because even a 1 million token window has hard physical limits. I mean, it equates to perhaps 50 standard text-heavy business documents at one time.
And TechCorp is sitting on 500 gigabytes.
Right. You simply cannot force-feed an entire corporate infrastructure into a single prompt. It is physically impossible to fit.
But let's pretend for a second that we could. Let's say TechCorp only have one massive 300-page operational manual, and we just drop the entire PDF right into the prompt box. The source highlights a totally different, much more insidious problem that arises here.
Yes, the attention problem.
Right. It isn't just about storage capacity. It is about the degradation of the AI's attention span.
If we connect this to the bigger picture, you are hitting on a fundamental limitation of the transformer architecture itself. Just because an LLM has a large short-term memory does not mean it can perfectly synthesize and weigh every single piece of information held within that memory equally.
The masterclass uses this deceptively simple logic puzzle to prove this point, and I want to try it out on you.
Okay, let's hear it.
Let's imagine I type this exact prompt into an AI. Sally and Bob own an apple farm. Sally has 14 apples. Apples are often red. 12 is a nice number. Bob has no red apples, but he has 2 green apples. Green apples often taste bad. How many apples do they all have?
The mathematical answer is obvious to a human. Sally has 14 apples. Bob has 2 apples. They have 16 apples in total.
Exactly 16.
Mm-hmm.
But to the AI's internal attention mechanism, all that extra narrative flavor, the red skin of the apples, the subjective taste of the green ones, the bizarre injection of the number 12, all of that acts as cognitive friction.
It acts as noise, because when the transformer processes that text, it calculates mathematical weights between every single token to determine relevance. The question solely requires isolating inventory numbers. The taste and color are statistically irrelevant. So when you stuff a context window full of thousands of pages of corporate legalese, marketing jargon, and obsolete IT protocols, you are flooding the attention mechanism with an ocean of irrelevant noise.
And it just gets lost in the noise.
The AI has to burn computational power sifting through that noise to find the actual signal. As the noise increases, its reasoning capabilities measurably degrade. It begins to hallucinate or, focus on the wrong paragraphs entirely.
I am so glad we were talking about this because I really have to push back on the broader tech industry's current obsession with simply buying a bigger context window to solve enterprise AI problems.
It's a very common misconception.
It feels like throwing raw horsepower at a problem that requires a steering wheel. It's like, imagine I ask you to calculate complex long division in your head. Even if you possess a genius-level intellect and can easily hold all those numbers in your working memory, if I am standing 3 inches from your ear screaming random trivia about 19th century agriculture while you try to do the math, your concentration is going to shatter. The presence of the noise inherently corrupts the processing of the signal.
That is exactly it. Overwhelming the processing capability with irrelevant data is a guaranteed path to poor AI performance.
So if TickCourt's 500 gigabyte hard drive would essentially give our AI amnesia, blow up our API budget, and drown its attention span in irrelevant noise, we are left with a massive filtering problem.
A huge one.
We cannot give it everything. We only want to give it the exact 3 paragraphs that actually contain the answer to the employee-specific question. But how do you search a half terabyte of data for meaning rather than just looking for keywords?
Well, you have to completely abandon traditional search architecture. You need a search engine that operates on a fundamentally different plane than the SQL databases we have relied on for the last 30 years.
The source makes a really compelling case for why traditional keyword search is so broken in corporate environments. Think about a standard internet portal. A stressed employee logs in and types vacation policy into the search bar.
Right.
In a traditional setup, that search bar is wired to a database query that scans every document looking for a direct match for the exact string of letters VACATION.
And if the Human Resources Department happened to title their official document Staff Time Off Guidelines or Annual Leave Protocols, what happens?
The search instantly fails. It returns 0 results.
Yep.
And the employee assumes no policy exists. The source points out that in sprawling corporate environments, these rigid, literal keyword searches fail upwards of 60% of the time.
That is an astonishing failure rate. And to combat that historically, developers had to write agonizingly complex rules. They would write endless wildcards, synonyms, and variations into the back-end code.
Like trying to predict every possible word.
Exactly, searching for vacation, holiday, leave, time off, desperately hoping to cast a net wide enough to catch the document. It puts the entire cognitive burden on the user to magically guess the exact vocabulary the original author used 5 years ago.
Which is a remarkably hostile user experience.
It really is.
To fix it, we have to stop searching for letters and start translating meaning into math. We have to talk about embeddings.
Embeddings represent a total paradigm shift in data storage. Instead of storing a document as raw text characters, an embedding model reads a sentence, analyzes its semantic meaning, and converts that abstract meaning into a highly specific mathematical vector.
I want to make sure we don't lose anyone here. When you say a vector, we are literally just talking about a very long list of numbers, right?
That is all it is, an array of floating point numbers. Typically, in modern systems, these vectors consist of 1,536 distinct dimensions.
Okay, my brain just stuttered. 1,536 dimensions. We live in a 3D world. What does a 1536-dimensional space even mean in practical, functional terms?
It is helpful to visualize it by starting small. Imagine a simple 3D graph, x, y, and z axis.
Got it.
Let's say the x-axis represents royalty, the y-axis represents gender, and the z-axis represents age. If you plot the word king, it might sit high on the royalty axis, lean toward the male side of the gender axis, and lean older on the age axis. It occupies a specific physical coordinate in that 3D space.
Okay, I could picture a dot floating in a cube.
Now imagine doing that not with 3 axes, but with 1536 axes simultaneously.
That is wow.
We cannot easily label all 1536 dials because the neural network learns them organically through training. One dimension might track how formal the text is. Another might track geographic proximity, emotional urgency, or financial context. Collectively, those 1,536 numbers represent the precise, microscopic semantic coordinate of a concept in an unimaginably vast mathematical universe.
So when an employee types the phrase employee vacation policy, that phrase passes through the embedding model and gets converted into a unique string of 1,536 numbers. Then the HR document titled Staff Time Off Guidelines gets passed through. Because the underlying meaning of those two phrases is almost identical, their strings of 1536 numbers are going to be mathematically almost identical.
They end up occupying the exact same neighborhood in that high-dimensional space, regardless of the fact that they share 0 actual letters in common.
But a standard SQL database isn't built to store or compare massive arrays of 1536-dimensional coordinates, is it? We have to introduce a new piece of infrastructure here.
Right, the vector database. Platforms like ChromaDB, Pinecone, or Milvus. These are purpose-built systems engineered to ingest, store, and rapidly query millions of these complex vectors at scale. Now, when an employee queries the TechCorp chatbot, we are no longer asking the database to find matching words. We are asking it to calculate mathematical proximity.
The illustrative examples in the masterclass really cement this. An employee types into the chat, "Can I wear jeans to the office?" That question is instantly embedded into a vector. The database plots that coordinate and looks for whatever stored document is mathematically closest.
And it finds the policy.
Right, it pulls up the corporate dress code policy, even if the word jeans was never explicitly written by the HR department.
Or consider an IT use case. A user types, "I forgot my password and I'm locked out." The system mathematically maps the intent of that phrase directly to the account recovery and authentication protocols documentation. The system finally understands human intent.
When you actually run the code for this in the masterclass lab, you get a visceral sense of how it functions. You have to initialize an embedding model first, right?
The labs utilize a model called a sentence transformer, specifically an open source model like LLM. It is small, incredibly fast, and runs locally. You write a script that passes your queries and your documents through this transformer to encode them into vectors. Then, to actually find the match within the database, the system executes a function called cosine similarity.
Cosine similarity. That sounds like trigonometry trauma from high school.
Mm.
How does the database actually calculate which document is closest to the question?
It is a geometric calculation. Imagine 2 lines drawn from the center of our mathematical universe. One line points to the coordinate of the user's question. The other line points to the coordinate of a document. Cosine similarity simply measures the angle between those 2 lines.
Just the angle.
Just the angle. If the lines point in the exact same direction, the angle is 0, and the cosine is 1, a perfect semantic match. If they point in completely opposite directions, the cosine drops, indicating they are unrelated. The database simply sorts the documents by which angles are tightest to the query.
But wait, earlier we established a hard physical rule. You cannot shove a 500-page manual into an AI context window. Can I shove a 500-page manual into an embedding model to create one giant supervector?
You cannot. Attempting to compress the nuanced, multifaceted meaning of an entire 500-page book into a single 1536-dimensional coordinate results in a blurry, averaged-out mathematical mess.
It just muddies the water.
Exactly. The specific details get completely lost in the aggregate. You must fracture the document into smaller, easily digestible pieces before you embed them. In the industry, this is known as chunking.
This sounds fraught with peril. If I just write a basic Python script that acts like a digital meat cleaver, indiscriminately chopping the text every 500 characters, I am inevitably going to chop a sentence right in half.
Oh, absolutely.
If the cleaver falls in the middle of the word jurisdiction, the database ends up storing juris in one chunk and diction in another. The context is entirely destroyed.
A blunt fixed character cut is disastrous for retrieval systems. The masterclass emphasizes a critical technique to solve this, and it's called chunk overlap. Instead of severe disconnected cuts, you engineer a sliding window. You might configure your script to chunk the document every 500 characters, but you mandate a 100-character overlap with the preceding chunk.
Ah, I see the logic. The tail end of chunk A becomes the introduction to chunk B. It acts as a bridge, preserving the connective tissue of the thoughts.
It preserves the narrative context. And tuning those specific parameters is not trivial. It is a vital engineering task. The source explicitly highlights that migrating from a naive, blunt cut strategy to an intelligent, paragraph-aware chunking strategy with a carefully calibrated overlap ratio can improve the accuracy of database retrieval by almost 40%.
40%, that's massive.
It ensures that when the mathematical angle matches, the database pulls a chunk containing a complete, coherent, and usable thought.
There is another massive variable to consider here, though, and it's something the source brings up that I'll call the Florida dilemma.
Ah, yes. The implementation of similarity scoring thresholds. This is where the math meets human unpredictability.
Right, so imagine a Tech Corp employee asks the chatbot, does the company allow me to take vacation to Florida? The words Florida and vacation will score incredibly high on semantic similarity in the vector database because the concepts of travel, leisure, and that specific state are highly correlated in the training data.
The math checks out.
The database calculates a tight angle and pulls the company vacation policy. Perfect. But what if the employee asks a slightly different question? Can I take my secure company laptop with me to Florida?
The intent of the user has radically shifted.
Exactly. But the word Florida is still heavily weighting the query. The math might still attempt to pull the vacation policy because the spatial coordinates are still somewhat close. But the employee doesn't need to know how to log PTO. They need the IT security jurisdiction policy regarding crossing state lines with encrypted hardware.
This specific scenario highlights why configuring a vector database is not a plug-and-play operation. It requires significant, thoughtful, upfront engineering. You cannot just accept whatever document is mathematically closest.
You need rules.
You must establish strict similarity scoring thresholds. You have to program a rule that dictates unless the cosine similarity match registers higher than a 0.85 on our confidence scale, do not return the result to the AI. You must intentionally filter out those low similarity tangential matches so the user gets the rigid IT policy, not the breezy vacation policy.
I have to say, configuring all of this, writing the scripts to optimize chunk sizes, calibrating the overlap percentages, agonizing over the exact cosine similarity thresholds, isn't this a massive, unpredictable headache compared to the rigid certainty of just throwing data into a standard SQL database?
It is definitely more work up front.
I mean, SQL is inflexible, but you know exactly what you are getting. Building a vector database feels like establishing a corporate Dewey Decimal System based entirely on vibes rather than exact book titles.
A Dewey Decimal System based on vibes is remarkably accurate, if slightly terrifying way to conceptualize it. It is a serious architectural trade-off. The initialization and calibration of a vector database are undeniably more complex and require continuous tuning.
But it's worth it.
The payoff on the other end is a search engine that feels almost telepathic to the end user. It transcends vocabulary and understands their underlying intent.
Okay, let's take a breath and survey where we are with our Tech Corp build. We have our massive LLM brain, but we know its short-term memory is fragile and expensive. So we took all 500 gigabytes of our internal documents, fractured them intelligently using chunk overlaps, passed them through an embedding model to convert their meaning into 1536-dimensional math, and stored them securely in a ChromaDB vector database.
We have a solid foundation.
Now, when a user asks a question, our database can instantly mathematically locate the exact 3 paragraphs regarding international remote work. The search problem is officially solved.
The retrieval mechanism is in place, but now we have to integrate it.
Which means we need an assembly line to connect the database to the brain. How do we actually automate the process of getting the AI to read those 3 specific paragraphs and format an answer for the user?
We implement the most critical framework in modern enterprise AI, RAG, Retrieval Augmented Generation.
Let's break down those 3 words because they describe the exact chronological sequence of the assembly line.
Step 1 is retrieve. The user hits enter on their question. Our backend system intercepts that text, converts it into a vector, queries our ChromeNDB, and retrieves the top 3 most semantically relevant document chunks based on our strict similarity thresholds.
Okay, step 2 is augment.
We take those 3 retrieved paragraphs and programmatically inject them directly into the system, prompt into the AI's context window, placing them right alongside the user's original question.
So we're sneaking the answers in.
We are artificially augmenting the AI's baseline knowledge with our private, hyperspecific, and up-to-date corporate data.
And finally, step 3 is generate.
The LLM reads the user's question, analyzes the augmented context we just force-fed it, and utilizes its vast reasoning capabilities to generate a perfectly accurate response based exclusively on the provided data.
Which is brilliant.
The brilliance of our egg is that no costly fine-tuning or retraining of the underlying neural network is required. We are just giving it an open book test.
It sounds incredibly elegant in theory, but practically speaking, building that pipeline sounds horrifying.
Oh, it can be.
Writing the raw Python code to handle the user interface, authenticate with the embedding model API, manage the connection pooling to the vector database, format the retrieved text, and then orchestrate an asynchronous API call to OpenAI, managing the timeouts, the errors, the retries. That sounds like a fragile programming nightmare.
If you attempt to build a production RG system from scratch utilizing raw API calls and basic SDKs, it is a nightmare. The codebase becomes deeply convoluted very quickly. You are spending 90% of your time managing state, data schemas, and API quirks rather than building actual AI features.
Right, fighting the plumbing instead of building the house.
That intense friction is exactly why the industry almost universally adopted an abstraction layer called LangChain.
LangChain. This is perhaps the loudest buzzword in this space right now.
Yeah.
What does this framework actually do under the hood?
Think of LangChain as the ultimate standardization layer. It provides pre-built, highly optimized components and uniform interfaces that handle all of that underlying plumbing. In the masterclass lab, they demonstrate this with a striking visual comparison.
What's the comparison?
If you write the code to execute a basic, augmented AI call using the traditional OpenAI software development kit, it requires roughly 10 to 15 lines of dense boilerplate code just to format the request and parse the response.
And when you utilize LangChain,
It condenses those 15 lines of boilerplate into 3 incredibly clean, readable lines of code.
that level of efficiency is great for a developer's sanity, but the real superpower they highlight in the source material is the architectural flexibility it provides.
The vendor-agnostic nature of LangChain is its greatest asset. Imagine TechCorp launches their bot using OpenAI's GPT 3.5 Turbo. 6 months later, Anthropic releases a new Claude model that is twice as fast and half the price.
You'd want to switch immediately.
But if TechCorp wrote their application using raw OpenAI SDKs, migrating to Anthropic requires ripping out the entire backend infrastructure, rewriting the API integrations, and altering the data structures. It is a massive migration project.
So what does LangChain do differently?
If they built the application utilizing LangChain, because LangChain uses standardized universal interfaces, switching the foundational brain of the company from OpenAI to Anthropic is literally a one-word code change. You simply update the model name string in the initialization function.
That is wild. It completely removes vendor lock-in. You can swap out the most complex software on Earth like you're changing a light bulb.
It commoditizes the LLM layer, and the labs delve into another brilliant syntactic feature of LangChain that makes this possible, the pipe operator.
Oh, this is reminiscent of Unix pipes in
Yeah.
traditional command line programming.
It operates on the exact same philosophy. Normally, in a Python script, you would define a variable for your prompt template, then you would pass that variable into a function to call the model and assign the output to a new variable.
Then you pass that to the next thing.
Right, then you would pass that variable into a parsing function to clean up the text. LangChain allows you to chain all of these distinct components, the prompt template, the LLM, and the output parser together in one single elegant line of code separated by a pipe symbol. The data flows sequentially and automatically from one component to the next.
I want to focus on those output parsers for a second because the lab highlights their importance in enterprise software. AI, by its nature, is chatty. It loves to spit out conversational, free-flowing text. Sure, I can help you with that. Here's the data.
It's very polite.
But if we are integrating this AI into a broader software application, free text is a disaster. Our front-end application might need a perfectly structured JSON object or a clean Python list in order to render a table on the screen.
You cannot build reliable software on top of unpredictable conversational strings. That is exactly the problem LangChain's output parsers solve. They intercept the raw text generated by the AI and systematically force it into a rigid, structured format that the rest of your software architecture can actually digest and utilize programmatically.
Okay, here is where this architecture becomes mission critical. When we combine the retrieval power of RGAG with the orchestration of LangChain, we have an obligation to erect some serious guardrails. Because, despite all of this engineering, AI still possesses a terrifying habit of hallucinating, of confidently fabricating information when it doesn't actually know the answer.
And in a corporate environment, a hallucination is not a funny quirk. It is an unacceptable liability.
Seriously.
If an employee asks about severance packages and the HR bot hallucinates a policy offering 6 months of paid leave, TechCorp has a massive internal crisis on its hands.
So in the RGA lab, they explicitly demonstrate how to configure the system prompt to brutally suppress this behavior. You establish a non-negotiable rule at the top of the prompt. If the specific answer to the user's query cannot be found in the provided or retrieved context, you must respond exactly with the phrase, "I do not have sufficient information to answer that question."
It is a paramount constraint. You are actively commanding the model to suppress its inherent probabilistic urge to be helpful by guessing. Furthermore, a production-ready RAG system must be engineered to include source attribution.
Source attribution is huge.
Every single response the chatbot generates must include a verifiable citation pointing directly to the exact TechCorp document it extracted the answer from.
So the end user doesn't just have to blindly trust the machine. They can click a link, open the PDF, and verify the policy with their own eyes. Trust, but verify.
Transparency is the only way to drive user adoption of an AI system.
I have to admit, LangChain sounds like a miracle for developers. But it also sounds dangerously similar to hiring a general contractor to build your house instead of taking the time to individually vet and hire a plumber, an electrician, and a roofer. Yes, the general contractor makes your life infinitely easier. But does relying so heavily on LangChain make an engineering team too dependent on a middleman framework?
That's a fair concern.
If the framework introduces latency or has inherent limitations in how it handles specific edge cases, aren't we permanently stuck with those limitations?
That is a highly active and valid architectural debate within the engineering community right now. Whenever you utilize a heavy abstraction layer, you are making a conscious trade-off. You are sacrificing granular, low-level control in exchange for rapid development speed and ease of use.
Speed versus control.
For a company like TechCorp, whose primary goal is building an internal IT tool quickly, the speed to market provided by LangChain exponentially outweighs the loss of low-level control. However, if you are a specialized startup building a hyper-optimized, latency-sensitive AI product that needs to process millions of transactions a second, you might deliberately choose to bypass LangChain and write the raw API integrations yourself to squeeze out every millisecond of performance.
That makes perfect sense. Okay, so we have our flawless RAG pipeline, built, elegantly orchestrated by LangChain. The vector database retrieves the relevant paragraphs, the AI reads them, and it formulates an answer. But as anyone who has spent more than 5 minutes interacting with ChatGPT knows, sometimes you provide the AI with perfect, immaculate data, and it still spits out a weird, unhelpful, or poorly formatted response.
Because the AI is highly literal. The
Yeah.
quality and utility of the generated output are inextricably linked to the precise phrasing of the input.
Which means we have to master the art of the ask. We have to dive into prompt engineering.
How you instruct the model is just as structurally important as the data you provide to it.
The source material provides a glaring example of this. Imagine an employee types into the TechCorp agent, "What is the policy?" That is it, just 4 words. The vector database is going to panic, retrieve a chaotic mountain of irrelevant documents ranging from dress codes to data retention, and the AI is going to generate a massive wall of useless text because the request lacked any specificity. But if the employee is guided to ask, "What is the company's remote work policy specifically for international employees residing in the EU?" the system zeroes in on a targeted, highly accurate result.
But prompt engineering goes far beyond merely encouraging users to be specific. For the developer, it is about systematically and programmatically controlling the agent's behavior behind the scenes. The Masterclass Lab meticulously breaks down prompt engineering into 4 specific, structured methodologies.
We need to explore these because they represent the evolution of how we communicate with machines. The baseline technique is zero-shot prompting.
Zero-shot is the most common interaction method. It is when you demand the AI perform a task without providing it with any prior examples of what a successful output should look like. You are relying entirely on the model's pre-existing foundational training and the raw clarity of your instructions.
The lab demonstrates the danger of vague zero-shot prompts. If you just tell the system, write a privacy policy, it will generate a meandering, generic essay.
Very generic.
But if your zero-shot prompt is engineered with intense specificity, write a 200-word GDPR-compliant privacy policy targeted at European consumers, mandating a strict 30-day data retention period using a professional but accessible tone, you receive a focused, highly usable document on the first try.
Specificity and constraint are the defining factors of success in zero-shot prompting. You basically have to box the AI in.
If zero-shot fails, we escalate to technique 2, one-shot prompting.
In one-shot prompting, you supply the AI with a single, perfectly formatted example, a template within the prompt itself, specifically to enforce a desired structural output.
The lab example for this is incredibly practical. Let's say TechCorp needs the AI to draft a new remote work policy. If you rely on zero-shot, the AI will invent its own formatting, maybe bullet points, maybe Roman numerals.
It's a coin toss.
But if you provide the AI with a single example of a completely unrelated document, say an old corporate refund policy that happens to be neatly divided into 5 very specific, standardized sections with standardized headers, and you instruct the AI, draft the new remote work policy strictly following the structural format of this refund policy, the AI will strip the formatting from the example and apply it perfectly to the new content.
Precisely. One-shot prompting is not about teaching the AI new facts. It is about establishing a rigid structural baseline so your outputs are consistently formatted.
Which naturally progresses to technique 3, few-shot prompting.
Few-shot goes a step further in complexity. Instead of providing one example for structure, you provide multiple examples, 3, 5, sometimes 10, to teach the model subtle nuances like tone, cadence, and brain consistency.
This is an absolute game changer for building customer service bots. The lab has you feed the AI 3 distinct examples of highly empathetic, de-escalating replies written by your best human customer support agent. By mathematically analyzing the patterns across those 3 examples, the AI learns the specific voice of the company.
It essentially calibrates the model's emotional intelligence for that specific conversational session. It learns that TechCorp responds to anger with measured empathy, not robotic apologies.
But the most fascinating technique, the one that really feels like unlocking a new level of computing, is number 4, chain of thought prompting.
Chain of thought is revolutionary because it actually forces the artificial neural network to mimic the step-by-step reasoning process of a human mind.
The source dives deep into a complex example to illustrate this. Let's say TechCorp needs to audit and overhaul its internal data retention policy. If you use a zero-shot prompt and simply command, fix our data retention policy to be compliant, the AI will instantly try to generate the final policy, essentially guessing at the necessary changes.
And it will fail.
It will likely miss critical logical steps. But with chain of thought, you explicitly mandate the reasoning steps it must complete before it is allowed to generate the final answer.
You build a cognitive scaffold for it. You instruct it. Step 1. Thoroughly review the current GDPR regulations regarding data retention. Step 2. Analyze our existing TechCorp policy text to identify specific compliance gaps. Step 3. Research standard industry best practices for mitigating those gaps. Step 4. Only after completing the previous steps, draft specific, actionable recommendations.
And the critical part is that you force the AI to visibly output its work for each of those intermediate steps.
Right.
Why does forcing it to show its work actually result in a vastly superior final answer computationally?
Because you are manipulating how the transformer architecture predicts tokens. Large language models operate sequentially. They generate the next most mathematically likely token based on the entire preceding context window. When you force the AI to write out its detailed analysis in step 2, that generated text physically becomes part of the context window. When it moves to step 3, it is now utilizing its own prior reasoning to inform its next prediction. You are forcing it to build a robust foundation of logic before it attempts to place the final roof on the building. It significantly decreases hallucination and increases accuracy on complex, multi-layered tasks.
I love this concept so much because it perfectly mirrors human management. It reminds me of managing a brilliant, eager, but incredibly literal-minded intern.
That's a great way to think about it.
If you just toss a file at the intern and say, make a report, they will panic and hand you a disorganized mess of disjointed thoughts. But if you sit them down, give them a rigid template, show them 3 examples of successful past reports, and give them a step-by-step checklist of how to conduct the research, they will hand you absolute gold.
That is the perfect analogy for prompt engineering. You are not magically making the model smarter. You are designing an operational framework that allows a literal-minded intellect to succeed.
So, taking stock of our TechCorp project, this is amazing. We have built a remarkably intelligent, highly accurate Q&A bot. An employee asks a question, the system searches the vector database, retrieves the perfect context, follows our meticulous prompt instructions, and delivers a flawless, cited answer.
It works perfectly.
But at the end of the day, it is still just a static chatbot sitting in a window. It can only answer questions. What if a user's request requires the AI to actually do things? To execute a sequence of actions, make autonomous decisions, evaluate its own work, and loop back if something goes wrong.
You have identified the exact threshold where an application evolves from a simple tool into an autonomous agent.
And navigating that threshold brings us into the realm of LangGraph. We are moving beyond the linear chains of simple LangChain.
Simple LangChain architectures are strictly linear. They execute step A, which feeds into step B, which feeds into step C, and then the program terminates. But TechCorp's actual business requirements are rarely that clean.
Business is messy.
Real corporate workflows are messy. They require multi-step processes, conditional branching based on variable outcomes, and iterative loops. LangGraph is an advanced framework that transforms that linear sequential code into a dynamic, stateful graph.
To understand how this works, we need to define the three structural components of this graph: nodes, edges, and the state graph.
A node is the fundamental building block. It is simply an individual unit of computation. In technical terms, it is a discrete Python function designed to execute one specific task.
So a node might be a function titled gather documents or a function titled evaluate compliance.
Exactly. The second component is the edges. Edges are the directional connections between the nodes. They act as the traffic controllers, defining the execution flow. When node 1 finishes, the edge dictates whether the system should route to node 2 or node 3.
And the third component, the state graph.
This is the most crucial innovation of the framework. The state graph is a shared, persistent memory that exists across the entire workflow. As data is processed and generated, it is passed from node to node and stored in a highly structured format, typically a Python typedict.
So they share a brain.
Essentially, yes. This means that if the workflow reaches node 5 can instantly access and utilize data that was originally retrieved back in node 1. The agent maintains a memory of its own actions.
To make this abstract concept concrete, let's walk meticulously through the primary illustrative example provided in the source. We are going to build an autonomous GDPR compliance loop for TechCorp using LangGraph.
Let's trace the execution path. A compliance officer asks the system to evaluate the overall EU data privacy compliance of a specific department. The LangGraph workflow initiates at node 1.
The sole job of Node 1 is to execute a search against our vector database and gather every single privacy policy document related to that department. Once it compiles that raw list of documents, it saves that list onto our shared clipboard, the state graph. Then an edge routes the flow to Node 2.
Node 2 accesses the state graph, takes those documents, and performs a computational extraction. It strips out the formatting, extracts the raw text, cleans it up, and saves the sanitized text back to the state graph. The edge then routes the flow forward to node 3.
Node 3 is where the LLM brain actually kicks in. It takes that massive block of clean text and evaluates it against current GDPR regulations, ultimately calculating a numerical compliance score out of 100. It writes that score to the state graph. Now here's the aha moment of LangGraph. Between node 3 and the next step, we don't just have a standard edge, we have a conditional edge.
This is where we inject decision-making logic into the flow. The conditional edge inspects the compliance score that node 3 just saved to the state graph. We program a rule. If the score is below 75%, the system does not just stop, and it doesn't just spit out a generic failure message to the user. Instead, the conditional edge routes the execution flow backward to node 1.
A loop. It essentially tells node 1, hey, the documents you found didn't contain enough robust policies to achieve a passing score. Go query the database again, but this time use slightly broader search parameters to see if you missed any supplementary documents.
It acts autonomously to rectify its own failure. But if the initial score calculated by node 3 is above 75%, the conditional edge evaluates the rule, sees it passed, and routes the flow forward to node 4 to conduct a deeper gap analysis, and finally to node 5 to generate and email a comprehensive, formatted report to the compliance officer.
This represents a monumental shift in how we interact with computers.
Yeah.
We aren't just querying an LLM like a glorified encyclopedia anymore. We have constructed a true agent. It has autonomy to make decisions, it possesses persistent memory through the state graph, and crucially, it has the ability to use external tools.
The lab provided in the masterclass demonstrates this tool use capability brilliantly. They guide you through building a router node. The sole purpose of this node is to inspect the user's initial query and decide which tool is required to solve it.
So it's like a dispatcher.
Exactly. If the user asks a complex mathematical question, say, calculating compound interest on a corporate loan, the LLM knows it is inherently bad at math. So the router node dynamically routes the execution flow to a specialized Python calculator node to perform the math flawlessly.
And what if the user asks a question about breaking news or current events that obviously isn't contained within TechCorp's static internal database?
The router node recognizes the knowledge gap and routes the request out to a DuckDuckGo web search node. The agent performs a live internet search, reads the results, saves them to the state graph, and then uses that fresh data to formulate an answer. The agent is autonomously orchestrating an entire suite of tools based entirely on its own assessment of what is necessary to fulfill the human's request.
I have to interject with a serious operational pushback here. This looping mechanism we discussed in the GDPR example, the system automatically routing back to node 1 if the score falls below 75%, what is the risk of triggering an infinite loop?
It's a huge risk.
If TechCorp simply does not possess the necessary documents to ever reach a 75% score, does the autonomous agent just spin its wheels in the background forever, constantly searching, constantly failing, and quietly racking up a catastrophic API bill that bankrupts the IT department?
That is not just a hypothetical risk. It is a very real, very expensive danger inherent in agentic architecture. An unconstrained agent is a financial liability. In practical production environments, developers must program strict circuit breakers into the conditional edges. You must define a hard maximum recursion limit.
So you tell it to stop eventually.
Right. You explicitly instruct the system you may loop back to node 1 a maximum of 3 times. If you fail to achieve a 75% score on the 4th attempt, break the loop and route the flow to a human intervention node, alerting a manager.
Okay, that makes me feel much better. It really feels like LangGraph is the equivalent of giving the AI a physical flowchart and a clipboard.
Oh.
It carries the clipboard, which is the state graph from station to station, performing the required work, making dynamic decisions based on the branching paths of the flowchart, and meticulously filling out the paperwork on the clipboard as it progresses.
That is a highly accurate, very tangible way to visualize the architecture.
Okay, so we have equipped our TechCorp AI with a flowchart, a calculator, and live web access. But TechCorp isn't just a collection of PDFs and math problems. They are a living enterprise. They have sprawling, proprietary external systems. They have a massive inventory database in PostgreSQL, a complex customer support ticketing system like Jira, a communication hub on Slack, and a code repository on GitHub. How on earth do we connect our elegant LangGraph agent to all of those disparate systems without forcing our engineering team to spend the next 6 months writing a million lines of custom API integration code?
This dilemma brings us to the final and perhaps most revolutionary piece of the modern AI puzzle. We are talking about MCP.
The Model Context Protocol. This was released by Anthropic late last year, and it has been making massive waves. What foundational pain point does this actually solve for developers?
To understand the solution, you must deeply understand the pain of the old way. Historically, if you wanted your AI agent to talk to a SQL database, a human developer had to sit down and manually write custom API integration code, specifically bridging your AI framework to that exact SQL endpoint.
That sounds incredibly tedious.
It is. You had to manage the authentication headers, parse the specific JSON structure the database expected, and handle the specific error codes it returned. It is rigid, highly brittle work. And the moment the database vendor updates their API, your custom integration shatters and your AI agent breaks.
So how is MCP functionally different? The source material states that it functions similarly to an API, but it provides self-describing interfaces. What does that actually mean in plain English?
This raises a profoundly important question about the philosophy of system integration. Traditional APIs require the human developer to understand all of the intricate implementation details, what headers to send, what data types to use. MCP entirely flips that script. An MCP server essentially exposes a tool to the network, and alongside that tool, it broadcasts a standardized self-describing schema.
It tells you what it does.
It essentially announces to the network, "Hello, I am a customer database tool. Here is a description of exactly what I do. Here are the 3 specific inputs I require, and here is the exact format of the data I will return."
So instead of the human developer agonizing over the logic for how to format the endpoint request, we simply expose the tool via the MCP protocol, and the AI agent autonomously reads that self-describing schema and figures out how to use the tool on the fly.
Precisely. The cognitive burden of understanding the integration shifts entirely from the human developer to the AI agent.
The source provides a fantastic illustrative example of this in action. Let's imagine a frustrated customer asks the tech court chatbot, "What is the shipping status of my order? Number 1234."
In a traditional system, the AI would be helpless. But in an MCP-enabled architecture, the LangGraph agent parses the request and realizes it needs live order information. It scans the available network and sees that a customer database MCP is active and broadcasting its schema. The agent autonomously formats a query requesting order 1234 according to the schema's rules, sends it to the MCP server, ingests the return data regarding shipping status, and formulates a polite conversational response for the user.
The Masterclass Lab actually shows you how incredibly simple this is to build using a library called FastMCP. You essentially just write a standard basic Python function to query your local database, and then you just drop a simple decorator at mcp.tool right above the function.
Yes. That single line of code, that decorator, wraps your basic Python function in the standardized MCP protocol. Once you execute that server script, any MCP-compatible agent on your network can instantly see, understand, and utilize that function as an autonomous tool.
But the true world-changing power of this protocol, as the Masterclass points out, isn't just about you writing your own custom MCP servers for your internal databases. It is about the open source community.
Exactly. Because the protocol is standardized, you don't have to write the code at all. Developers worldwide have already written, heavily tested, and are actively maintaining robust MCP servers for almost every major platform. GitHub, GitLab, PostgreSQL, Slack, Google Drive, Jira, the servers already exist.
So if the CEO of TechCorp decides tomorrow that he wants the AI agent to be able to read and analyze the company's entire software code base on GitHub, our developers do not have to spend a week reading the dense GitHub API documentation.
Not at all.
They just download the open source GitHub MCP server, plug it into the network, and boom, the AI agent can instantly, autonomously read repositories, analyze commits, and summarize code changes.
It creates literal plug-and-play functionality for artificial intelligence.
So what does this all mean? The source material literally uses the analogy so that MCP is a universal USB port for AI, which is a brilliant, highly evocative analogy. But I have to push back hard on the terrifying security implications of that analogy.
I was wondering when we'd get to security.
If I find a random universal USB drive in a parking lot and plug it into my corporate laptop, I could inject a devastating virus into the network. If this AI agent has autonomous plug-and-play access to our company's live production SQL customer database, what stops the agent from getting confused during a complex query and accidentally executing a command that drops our entire customer table, erasing our business?
This exact fear represents the absolute critical security frontier of modern AI engineering. The source material briefly but urgently touches on this at the end when discussing deploying production-ready packages. You absolutely cannot blindly grant an autonomous AI agent unrestricted write access to your production databases. It is architectural suicide.
So what do you do?
When you configure the MCP servers, you must lock them down with strict, immutable read-only permissions wherever possible.
But what if the business workflow actually requires the agent to execute a change? What if the goal of the agent is to process and initiate a customer refund? It has to write to the database.
In those high-stakes scenarios, you must implement what is known as a human-in-the-loop approval flow within your LangGraph architecture.
A human in the loop.
The AI is permitted to do all the heavy lifting. It gathers the customer data, verifies the return policy, and prepares the exact database command required to initiate the refund. But before it can execute, the workflow forcefully pauses. An automated notification, perhaps via a Slack MCP, is sent to a human financial manager containing the proposed action.
So it asks for permission.
Exactly. The human reviews the agent's work, clicks approve, and only upon receiving that cryptographic human approval does the agent proceed with the execution.
Okay, that makes me feel slightly less terrified of our new robotic overlords. It keeps a human hand firmly on the steering wheel.
It is about engineering governed autonomy. You want the speed of the machine with the accountability of the human.
Well, this brings us to the end of our build. Let's take a deep breath and recap the incredible, towering architecture we have just constructed for TechCorp.
It has been an incredibly comprehensive journey from raw data to autonomous action.
We started with a deeply frustrated TechCorp employee who who probably used to waste 30 minutes manually clicking through deeply nested intranet folders, frantically searching 500 gigabytes of PDFs just to find a single paragraph about international travel policies.
And we systematically solve that bottleneck by applying vector databases and embeddings, fundamentally transforming the search process from matching static keywords to locating mathematical meaning.
Then, we constructed the RAG architecture retrieval augmented generation to intercept those perfect search results and seamlessly inject them directly into the short-term memory of a massive large language model.
We orchestrated that entire complex pipeline elegantly and efficiently, avoiding brittle API code by utilizing the standardized abstractions of LangChain.
We implemented rigorous prompt engineering, specifically leveraging advanced techniques like chain of thought to force the AI to reason logically, show its work, and format its answers perfectly for our software to digest.
We then radically upgraded the system from a static reactive chatbot into a dynamic, autonomous agent utilizing LangGraph, granting it persistent stateful memory and the ability to autonomously loop through complex multi-step workflows to correct its own errors.
And finally, we deployed the Model Context Protocol, MCP, equipping our agent with a universal USB port, connecting it seamlessly to external databases, live web searches, and real-world corporate tools. Now, that same agonizing 30-minute manual search takes less than 30 seconds. The answer is perfectly formatted, mathematically accurate, and fully sourced back to the original document.
But the true underlying takeaway here isn't just a massive speed upgrade for an HR query. It is a fundamental paradigm shift in how an enterprise operates. By deeply integrating these disparate technologies, we have shifted the organization from passively relying on static, dead documents to actively interacting with a living, interconnected, intelligent system.
It essentially changes the entire definition of what corporate software is.
Exactly. With the combination of LangGraph's autonomy and MCP's connectivity, the agent doesn't just wait passively for a human to ask a question. It possesses the architecture to become proactive. The source material concludes by explicitly pointing toward the near future of predictive analytics and proactive compliance agents.
Right. If the LangGraph agent is continuously, quietly scanning the internal HR database in the background and seamlessly cross-referencing those policies with newly passed legal regulations via its DuckDuckGo web search tool.
It can independently identify a critical compliance gap, draft a highly specific recommended policy update, and write it to the legal department for review before a human employee ever even realizes the company is out of compliance. It solves existential corporate problems before the question is ever asked.
Which leaves me with a final, slightly provocative thought for you to ponder as we wrap up today's journey. If we can truly build a stateful, persistent LangGraph agent and connect it via MCP to every single system, database, communication channel, and workflow within a company, at what point does the AI fundamentally stop being an assistant that you occasionally ask for help and start becoming the digital manager that continuously analyzes the holistic state of the business and proactively tells you what needs to be fixed today?
That is the exact transformative horizon the industry is accelerating toward.
It is a fascinating, awe-inspiring, and maybe just slightly intimidating future. But at least now you know exactly how the engine works under the hood. You aren't on the outside looking in anymore. Thank you so much for joining us on this deep dive. We will catch you next time.